So 1.3, errors and uncertainties. Okay, so first of all, you need to go through systematic error. So they say it's a constant error in one direction. So it means the error is always bigger than the actual value or always smaller than the actual values. Okay, so for example, zero error. Zero error is the systematic error. Okay, example, zero error. Okay, so zero error is where you are not measuring anything, but it shows reading. So let's say your weighing machine. So your weighing machines, you are not measuring any weight, any mass, or any object, but it's supposed to show 0 kg, for example, but at the end it shows 0.1 kg. Okay, whenever you turn it on, it shows 0.1 kg. So that is a systematic error where it shows value that is always bigger than 0. Okay, so always too small can be a negative value. Okay, so something like that cannot be eliminated by repeating or averaging. So that means if you do measurement for many times, the systematic error is still there. Okay, so you cannot do many find average. It doesn't help. Okay, so if systematic error is small, then measurement is accurate. It's accurate. So let's say the zero error is just 0.01 kg. So it is still somehow accurate. Okay, so of course, the best way, you know, you cannot eliminate by repeating or averaging, but you can eliminate it by subtract away the zero error. So there are ways to do correction on that. Okay, then the next one, accuracy, refers to degree of agreement between results of a measurement and true value of quantities. Okay, so that means how accurate is a value, right? So it depends on what instrument you use. So for example, if you are using measuring tape, maybe not so accurate. It's like 1 mm only. Okay, so the smallest scale is 1 mm. Okay, if you're using maybe vinyl caliper, it is more accurate. Or you want to be more accurate, you can use micrometer screw gauge. So the accuracy increase if you use an instrument with a better accuracy. Okay, so it will get closer to the true value. Okay, now let's see random error. So the random error is random fluctuations. Compared to this, this is one direction. This is random fluctuations. So that means sometimes it's too big, sometimes it's too small. Okay, so it can just randomly distributed around the true value. Okay, random fluctuation or scatter about the true value can be reduced by repeating and averaging. So imagine it's sometimes too big, sometimes too small from the true value. So if you find the average, if you do it for a few times and you find the average, then the random error is overcome. So that's why they say can be reduced by repeating and averaging. When random error is small, measurement is precise. So the idea of precise is here. Precision refers to degree of agreement of repeated measurements of the same quantity, and regardless of whether it is correct or not. So in a more simple words, that means precise, the measurements are precise when they are close to each other. So for example, this one, they are close to each other, then it is precise. If they are not close to each other, then it's not precise. Okay, so this is precise. The precision is good. Okay, so this is also good precisions. Okay, so accurate. Accurate must be close to the actual value. This is good accuracy. So because they are close to the red line, which is the true value. Okay, so this one, accuracy is bad because they are far away from the true value. So this one, far away from the true value, so it's bad accuracy. So you can see the comparison between accuracy and precision in this way. So precision is they must close to each other. Accuracy must be close to the true value. So that's the difference. So this part is about the errors. So you want to calculate errors, there are a few formula here. Now for the example, let's say a quantity x, which is 2.0 plus minus 0.1 mm. So first of all, we need to know that 2.0 is the x, the plus minus delta x, plus minus 0.1 is the delta x. Delta x is known as the absolute uncertainty. Absolute uncertainty is delta x is plus minus 0.1 mm, which is this part, the back one. So from here, you can find out the fractional uncertainty. So to find out the fractional uncertainty, so basically what we do is we take the 0.1, the delta x 0.1 divide by 2, and then you get, divide by x, right? X means 2. 0.1 divided by 2, then you get 0.05. So you get fractional uncertainty. So that's fractional uncertainty. But if you want to find percentage uncertainty, so we just take the fractional uncertainty, multiply with 100. And then you take this, multiply with 100, you get 5. You write it as 5%. Okay. Now, combining errors. Sometimes we have to add the values, we have to subtract the values. Okay, then how the errors works. So we do it like this. Add absolute error. We add the absolute value, the error. We add the absolute errors. Okay, so no matter you are adding the values or you are subtracting the values, for the error, we just add them up. Okay, now example. If p equal to 2x plus y over 3, our formula is this. Or our formula is p equal to 2x minus y over 3. No matter it is adding or subtracting, you can see here, plus or minus. To find the error, we always plus. We always plus 2 delta x plus delta y over 3. So we always plus. So for the error, we always plus. Okay, so no matter the formula is plus or minus, we always plus the error. Okay, to make it clearer, we take more example. Okay, so let's see here. We come to this part straight away for temporarily. We'll go back to the previous part later. Okay, so case 1. When you add or subtract quantities in an equation, absolute uncertainty of each value is added together. And that is what you heard just now. No matter the formula is adding or subtracting, we just add up the absolute uncertainty. Okay, so we take one example here. The length of copper wire at 30 degrees Celsius is 18.2 plus minus 0.04 cm. And at 60 degrees Celsius, 19.7 plus minus 0.02 cm. Find the absolute uncertainty and the extension of the wire. Okay, so first of all, we look at extension of wire. Extension of the wire. Okay, so from here, we try to figure out the equation. So extension, let's say I call it E, equal to the final length minus the initial length, L2 minus L1. So the formula is E equal to L2 minus L1. So it seems like the quantity are subtracting here. Okay, so then we need to know that the absolute uncertainty we add up. Okay, so we have two parts. We have E we minus. We take 19.7 minus with 18.2. So we get this one, we get 1.5. 1.5. But for the absolute uncertainty, we add up. So we take the 0.02, add up with 0.04. Okay, so 0.02, add up with 0.04. So we get 0.06. Now, at the end, we write the answer as 1.5 plus minus 0.06. Yeah. So from here, you can see the actual value we minus, but the error we add up. Okay, so that is the idea. The first. Okay, now let's continue. Okay, so we have more techniques here. The second technique, when values multiplied or divided. That means when the formula involving multiplication or division, we add the percentage errors. Okay, we add the percentage error. So how to add the percentage error? Let's see example. Okay, let's see example. Okay. Case 2. When you multiply or divide quantities in an equation, percentage uncertainty of each value is added together. Okay, so same with what you saw in the previous part. Now we see the example. The weight of an iron block is 8.0 plus minus 0.3 Newton and is placed on a wooden base of area 3.5 plus minus 0.2 meters square. Find the percentage uncertainties of the values and then calculate the pressure exerted by the block. Okay, so first of all, let's think of the formula. Pressure equal to force over area. So the values are dividing. So the values are dividing, the quantities are dividing, but we need to add up the percentage error in order to find the absolute uncertainties. Okay, so let's divide first. The force is the weight. The weight here is the force, 8.0. The area, 3.5. Okay, so 8.0 divided by 3.5, we get 2.3. 2.3, okay. So let me put it in more decimal places for temporarily. So 8 divided by 2.8 divided by 3.5. 2. I put it in more decimal. 2.2857 and so on. Okay, so there are many decimals. And okay, now let's look at the percentage uncertainties. for the force as well as the area. Percentage uncertainty, percentage uncertainty for F, or the weight. So we find it 0.3 over 8.0 times 100. Okay, then we get a percentage as 0.3 over 8 times 100, 3.75%. So percentage uncertainty for error, for area, 0.2 over 3.5 times 100. Okay, 0.2 over 3.5 times 100. So we get 40 over 7, which is 5.71%. Okay. So based on the information here, we need to add up the percentage uncertainty. Okay, so we have to add up. So the percentage uncertainty for pressure is 3.75% plus 5.71%. Okay, we add up the percentage. So we get 9.46%. 9.46%. Okay, so after that, we need to know that the 9.46% that we get is the percentage uncertainty of pressure is equal to the delta P. Now I look back at the percentage uncertainty's formula over P times 100. Okay, so then I substitute a value 9.46 equal to delta P over the P 2.28 2.2857 times 100. Then I count my delta P then. 9.46 multiply with 2.2857 divided by 100. Okay, so I get 0.21622722. Okay, so how many significance are we going to take? So of course, there is a rules. There is a rules. So you see our delta P seems to be many decimal places. So the rule is, okay, let's look at the notes for temporarily. The rules is here. Significant figures. The absolute uncertainty or the actual error recorded to only one significant figure. One significant figure. Okay. And number of decimal places for a calculated quantity. Calculated quantity means the x. You know, we have x and delta x. So the x calculated quantity is the x. The actual error here is the delta x. Delta x, one significant figure. And then the number of decimal places for x is equal to the number of decimal places in actual error. So they are trying to say that x and delta x same decimal places. Same decimal places. Okay, so this is the concept. First, delta x, one significant figure. One significant figure. Second, x and delta x same decimal places. So that is the guidelines. The guidelines is like this. Okay, so during a practical, when calculating using a measured quantity, give answers to the same significant figures as the measurement or one less. Okay, so it depends on what instrument you use. So certain instrument can measure up to 2 decimal places, and then you put it in 2 decimal places, or you do one less decimal places, you round off. So that is what they say. Okay. Now our main concern is this part. Delta x, one significant figure, x and delta x, same decimal places. Okay, so we applied it here. That means the delta p, one significant figure. Okay, so we round off to 0.2. That is one significant figure. And the one significant figure here is one decimal place. So because of that, this one, we use one decimal place, 2.3. So at the end, we write our answer as 2.3 plus minus 0.2 Pascal. Okay,
Sure.
so this, yeah.
For percentage uncertainty, got any rules?
Percentage uncertainty, any rules? Not really, actually. You just need to remember the rule is we add up the percentage uncertainty. As in here, add up the percentage uncertainty. When the quantities divide, we add up the percent uncertainty.
Okay.
Yeah. So I saw some students that don't use percentage uncertainty, they use fractional uncertainty. It works also. Something like this. Okay, let's say I put in green color. If you are using fractional uncertainty, so you don't times 100, So you just take 0.3 divided by 8. 0.3 divided by 8, you get 0.0375 as fractional uncertainty. So this one, you don't multiply with 100. You keep it in that fractional uncertainty, which is 0.0571. Then you add up the fractional uncertainty. That means you add up these two. So you get 0.0946. Then after that, we don't use the percentage uncertainty. We use fractional uncertainty, which is 0.0946 equal to delta P over P. Then after that, you substitute with value. Delta P over this value, 2.28, 2.2857. And then you get a delta P. Okay, so 0.0946 times 2.2857. So you get you get the same value actually. You get 0.21622 and so on. So you round off to 0.2. And then you write your answer like this. So it works also. Some students that learn in college, they use this way, fractional uncertainty. But in books, they use percentage uncertainty. At the end, same. Okay, it's just with 100 or without 100 only. Okay, so that's the thing. Case 2. Now, let's see the third situations. Yeah, when values are powered, example squared. That means power 2, power 3, squared or cube. Multiply percentage error with power. So that means multiply with, if squared, you multiply with 2. Multiply the percentage error with 2. Okay, so let's say, you can see here, if r equal to 2x y cubed, or r equal to 2x over y cubed. So you see they are either the x and y are either multiplying or dividing. So no matter multiplying or dividing, we just add the percentage error. Then we just add the percentage error. But over here, we need to add the percentage error and at the same time times 3 because of the power 3 times 3 to the, they are using fractional uncertainty, if you can see that. And they are using fractional uncertainty, so times 3 to the fractional uncertainty. Okay. So of course, if you are using percentage uncertainty, then it is going to be like this. It's going to be like delta R over R times 100 as percentage uncertainty equal to delta X over X times 100 plus 3 delta Y over Y times 100. Okay. So that is where we are still applying the concept. We add up the percentage uncertainty, when the quantities are multiplying or dividing. Then we add up the percentage. Okay. At the same time, we multiply with 3 because of the power 3. So let's see example. Okay. Example. Okay, case 3. When you raise a measurement to the power n, the percentage uncertainty is multiplied by n. Okay, so same with the note just now. Suppose the length of a cube is given as 5.2 plus minus 0.2 cm. And you want to find the absolute uncertainty in the volume. Okay, so it's a cube. So we know that volume equal to the side power 3. Okay, now you find the volume first, the calculated quantity. So 5.7 to the power of 3. Okay, so initially we don't know how many decimal we want, so we just try to put as many as possible. 185.193. Okay, now the percentage. Percentage uncertainty. Okay, so percentage uncertainty for x is 0.2 over 5.7 times 100. This is the percentage uncertainty. Okay, 0.2 over 5.7 times 100. So we get 3.50877 and so on percent. Now, percentage uncertainty for V. So of course we need to times 3. Times 3 is 3 times the percentage uncertainty for x. So we times 3. So we get 10.526 and so on percentage. Okay, now we know the percentage uncertainty formula is delta V over V times 100. Then we find the delta V accordingly. 10.526 delta V. The V is 185.193. From the second row, we see that. Multiply with 100. And then we get a delta V. 185.193 divide 100. 19, no, 19 point. 19.494, 10.526 times 185.193 divided 100, 19.493, and so on. Okay, so again, we want to round off these to one significant figures. So rounding off these to one significant figure, we get 20. Get 20. So 20 is the nearest 10. Nearest 10. Round up to 10, the nearest 10. So then for this, we need to round off to the nearest 10 as well. So 190. 190. We round off, 190. So at the end, 190 plus minus 20 dm cube. Okay, so that is how we handle the power. Okay, so percentage uncertainty settled already. Again, just now I forgot to mention, if you don't want to use percentage uncertainty, you can always use fractional. So where this one, instead of using percentage, you don't want the 100, you use fractional uncertainty, then you get 0.0350877. Then this one you multiply with 3. Take this fractional uncertainty and multiply with 3. Then you get 0.10526. Then 0.10526 equal to delta V over V. 0.10526 equal to delta V over 185.193. And then you get delta V. You multiply that. So again, you get 19.493 and so on. You round off to the nearest 10, so which is 20. Okay, so after that, same answer.
Sure, I thought for calculated quantity, the number of decimal place will follow the number of decimal place in actual error.
Yes, correct.
Then, like for volume, our calculated value is 185.
Yeah, 185.
Got 185 from 193. So if follow the decimal place means 0 decimal place, which means doesn't that mean that it's 185 only?
We round off to the nearest 10 for this case because no decimal place to talk about for this case. It's not like this. We have a decimal place to one decimal. This is one decimal. This is easier, right? But this one, no decimal place to be used at all. And we follow what happens here. Round off. It's not the decimal place concept already. It's round off to one significant figures. So it's round off to the nearest 10. So this one round off to the nearest 10. So you don't apply the concept of the decimal place already.
Oh.
Yeah, so that's why we follow this way. Okay, so you can put this in the notes there when no decimal place is used at all. So we use round off. Okay, so the idea will be like this. Okay, then we settle already. Let's see what else. what else we have in the notes. Okay, so I've done everything here, and together with the errors. Okay, so it seems like we have done this part. Okay, so for these questions, let us discuss together. A double slit interference experiment is used to determine the wavelength of light from a monochromatic source. The following measurements are used. So we have slit separation A equal to this, fringe separation X equal to this, distance between slit and screen D equal to this. Okay, so they expect you to remember the formula for this. Okay, so the formula for the interference. Okay, so where the formula is actually this. I'm not sure whether you remember or not, so I just tell you straight away. Lambda equal to AX over D. So this is the formula. Okay, now what to do is when you look at this formula, right? First, you have to know our quantities are multiplying and dividing. Multiplying and dividing. Okay, so we need to add up the percentage error, if you still remember that. Okay, so first we work out the calculated quantity first. So A, 0.5, X, 1.7, D, 2.000. Okay, so we calculate this. Okay, so when you put the values inside, you need to be careful also, because there is a problem. They are using millimeter and meter. So because of that, we need to standardize. We need to standardize. We need to standardize everything to the same unit. So we have to add times 10 to the power of -3. And then we have to add times 10 to the power of -3 also. Okay, so the bottom one is okay. It's already in meter. So I change everything to meter. And then we get a certain value. Try to imagine something like that. Okay,
change
now
everything to millimeter.
can also. Everything in millimeter will be fine also.
Okay.
And you change the bottom one to millimeter. Okay, then the top one just remain. So, okay. The thing is, of course, I'm not going to count this because I know that I just want the percentage uncertainty of the wavelength. So that means we are not required to count everything to that extent. Okay, so we just do the next steps straight away. So the percentage error, percentage uncertainty, okay, let's say I write uncertainty lah. Error or uncertainty will be just fine. Percentage uncertainty for A 0.02 over 0.5 times 100. So we get 4%. Percentage uncertainty for X 0.1 over 1.7 times 100. So we get 5.9%. Percentage uncertainty for D 0.002 over 2 times 100. So we get 0.1%. So percentage uncertainty for wavelength. So we just need to add up the percentage. 4, 5.9, 0.1, 10%. Okay, so the answer is D. So like that. Huh? Okay. Now let's see the next question. So this question is a question involving square. Okay, let's see how we do it. They give us the percentage uncertainty straight away. So it saves our efforts in doing all that formula. So we can just, when they are multiplying and dividing, we need to add up the percentage. But if there is a square, we need to times 2. We need to times 2 to the 4%. So 6 plus 2 plus 2 times 4. 2 times 4 because of the square. Yeah, 16%. 16% for this case. Because of the 2, because of the square, we have to times 2. Without square, we just add up the percentage. So we get D for this case. Okay, now let's move on. Okay. So the question here is not in syllabus anymore. Okay, let us discuss this. 4 possible sources of error in a series of measurements are listed. Number 1, an analog meter whose scale is read from different angles. Okay, so imagine something like this. Your analog meter. Okay, so let's say the 0 is here. Okay, so and the reading 1, 2, 3, 4, 5, let's say. Okay, let's say the needle is pointing to 2. So if you look at it from the right, you may read maybe 1.9. You look at it from the left, you may read it as 2.1. If you look at it from the middle, you may read it as 2.0. So what am I trying to say is sometimes the reading can be smaller, sometimes the reading can be bigger, sometimes it can be accurate. So if there is a situation where it can be bigger or smaller, so this is what we call the random fluctuations. A random fluctuation is under the random error. So random fluctuation means it can be too big or too small. Okay, so under random error. This is under random error. Okay, number 1 is under random error. Okay, number 2, a meter which always measure 5% too high. So under one direction only. It is systematic error. Systematic error. Always too big. A meter which a needle that is not frictionless. So the needle sometimes stick slightly. Okay, so stick slightly. Sometimes stick slightly. Okay, so for this situation, it can be positive or negative. So because of friction, it can be positive or negative. And then because of that, it is under random error. random error. Number 4, a meter with a zero error. You know, zero error is systematic error. So which is like always too big, always a little bit more than zero, for example. So systematic error. Okay, so from here, we can see that 2 and 4, systematic error, 1 and 3, random error. So the answer is hence B. Yeah, so this is about error. Okay, so let's see another questions. Okay, these questions. The current in a block of semiconductors is 30.0 milliampere. When there is a potential difference of 10.0 volt across it, the dimensions of the block and the directions of the current in it are as shown. So they give us so many values. The electrical meters used are accurate to 0.1 milliampere and 0.1 volt. The dimensions of the block are accurate to 0.2 plus minus 0.2 mm. What is the resistivity of the semiconductor? So we need to know the formula of the resistivity. Okay, so of course, you may wondering, I haven't learned resistivity yet, how I know? Okay, so of course, our concern is not the resistivity formula. Our concern is how to count the error. So because of that, I just give you the resistivity error. If you learn that soon, resistivity error, resistivity formula is R, resistance, times A, the area, divided by L. Okay, so you will learn this formula in this particular form. R equal to resistivity L over A. You will learn it in this form, but later you need to rearrange it into this form in order to count the percentage error. Okay. So first we substitute and count the resistivity. Okay, so we have the, oh, no need to count. We just skip this because they always give 10.0, right? So no matter how, it's just 10.0. So you see, same value. So no need to count, just take 10.0. We focus on the absolute uncertainty. Okay, so find out the percentage uncertainty, percentage uncertainty of, okay, so I need to, they don't give us the resistance, right? So we need to use V equal to IR then. You know, V equal to IR, then R equal to V over I. R equal to V over I. Okay, our resistivity formula, the R become V over I. V over I. The I will go down. Okay, so our formula become this. Now, percentage uncertainty for V. Okay, so we have the 0.1 divided by the 10.0 volt times 100, 1%. Okay, then we have the percentage uncertainty for I, let's say, for I, the current is 0.1 milliampere, 30.0 milliampere. Okay, we just divide. times 100, 0.33%. So we have the area and the length. Okay, so we count the percentage uncertainty for the length. So it's given that the length is plus minus 0.2, plus minus 0.2. Okay, so for length, 0.2. So this is the length. Okay, the length is here. Of course, y is here, you will learn later. To count the area, we have to use this times this to get the area. So multiply to get the area. So the length is 15 times 100. Okay, then you get 1.33%. Okay, so for the area, so you know the area is just base times height, base times height. So let's say I further modify the formula to the area, I change to base times height, IL. Okay, so percentage uncertainty for the base, 0.2 over 15 times 100, 1.33. And percentage uncertainty for the height, 0.2 over 30 times 100. So we get 0.667. Okay, now we add up. So no matter they are multiplying or dividing, we just add up the percentage uncertainty. So by adding up all this, you get 4.67%. So 4.67% is the percentage uncertainty for resistivity. So we use the percentage uncertainty for 4.67, then it's going to be delta resistivity over resistivity times 100. Okay, then we substitute value. Delta rho. Resistivity is 10.0 times 100. So that means we get times 10 over 100, 0.467. So round off to one significant figure, 0.5. Okay, now we get the answer. 0.5, 10.0. So the answer is C. So any questions so far?
Oh, why this one so confusing?
There are too many quantities.
Yeah.
Yeah, too many quantities. But no matter how, the concept is, you imagine when you are really doing this, right? No need to write down all this one. So just set up the formula,
Mm-hmm.
and you can do all this in your calculator straight away, man. It's
Yeah.
just that when we discuss, I show one by one. So when you do multiple choice, who care about what calculation are you going to show, So who care? They just care about the final answer C. So this one you do in your calculator and add up percentage. then
No
then
matter if it's multiplication, subtraction, or like division, all those also just add together, right?
and just add together. Okay. The concept is like that lah. Just add together, but we add different thing, you see, like if the formula is something plus something, we add the absolute uncertainty straight away. But if the formula is multiplying or dividing, we add the percentage uncertainty. So we add different things. Okay. Now, settle already. Okay. So let's see. I let you try one question. After that, if we still have time, then we move on to the next topic. Okay, let's see the time first. Okay, so let me see a suitable question here. Okay. Now I'm going to write down the question straight away, but it's just a very short question. You see example. I have a rectangle. Okay, so the length is 3.0 plus minus 0.1 cm. I have the width 1.5 plus minus 0.1 cm. Okay, so you have to find perimeter P. Okay. So you have to put it in the same format together with the absolute uncertainty. Okay, so now you take a try for this. The idea is always add up, but there is a small difference between what to add. That is the things that I trying to say just now. Okay, so you see the notes first. Okay, it is true, we always add. But the thing is, when the formula involving additions or subtraction, we are not adding the fractional uncertainty. We add the absolute uncertainty. We add the absolute uncertainty. So I hope you see it in this way. I put extra notes for you. Okay, so this is the first technique. This is the second technique. This is the third technique. Okay, two important points. Add absolute uncertainty. Second important point, constant is included. What I mean by constant is included. You see, our formula have constant 2 and constant 3. The constant is still included in the calculation in the absolute uncertainty. Okay, compare. For technique 2 and 3, we add percentage or fractional uncertainty. So we add, but we add different things. Okay, we add fractional uncertainty. We add fractional uncertainty or percentage uncertainty. And the other thing is, you see we have 2 here. We have 2. In the calculation of the absolute uncertainty, the 2 is ignored. So constant is excluded. Okay, so let's come back to our question here. So we can easily know that the formula for parameter is 2 times length, 2 times W. So this is the additions of quantities. The additions of quantities, we have to add absolute uncertainty. Absolute uncertainty. Yeah, we are not adding the fractional uncertainty or the percentage uncertainty. We add absolute uncertainty. Yeah? So that's why the delta P, right? When you add, right? What we add is the 0.1 and the 0.1 straight away. And the other thing is constant is included. Constant is included. Huh? That means the 2 is included. 2, 0.1, the absolute uncertainty. No need to change to percentage. Huh? No need to change to fractional also. And the constant is included, 2, 0.1. And then we get 0.4. Delta P. The calculation of P, no problem. Is 2 times 3, 2 times 1.5, and then you get 9.0, right? So same decimal. Okay, so 9.0 plus minus 0.4 cm. So it should be like this. So you see, we can easily say that no matter how we add, but the thing is what you add absolute uncertainty or add fractional uncertainty, make yourself clear on that.